Okay, right, we're going to carry on with this, solving this question, example question 3.3, the backwater integration. And we need to set up a table to do all our calcs. So I'm just going to move down to the bottom of where we've got on the screen and start in a nice clean space to do the table of calculations. So we need to put some titles on here so we know where we are. Now I'm going to do a count, index, whatever we call it. We start, that first row will be 0. It'll be 1, 2, 3, etc. 0 the values that we know. X along the channel, and this is going to go negative. We'll start from 0, the end of the channel near the dam, and it's going to go backwards, so going to go negative. Y, the first value is, we can put that in from what we have up here, which was in the question. It said it's 5 meters at the dam site. We don't need to fix that. I actually put some units on here. It's good practice. Put units on all our things in Excel. Many people don't. It's good practice also to set the numbers of decimals. Now we don't want to go any less than millimeters, and certainly length we're probably too accurate in millimeters. In fact, in length I'm just going to change that from down to the millimeter to down to 0.1 of a meter, whereas depth, millimeters, it's too accurate. Centimeters probably the most precise you need to be, but we'll leave it to that for now. Now this is actually going to be an average value, so actually that's 5 is not quite right, so I'm going to put AVG for average after this so that we know what it is. And I'm just going to put at the top here Y start or Y naught. Let's call that Y naught because that's what we're doing in the numerical method. Y naught, and this will be the actual 5 value from our upstream. Right, again, let's get the units right. Okay, that's just how it is. That, and we're going to have a dy, the delta y that we have, and that's just up here. So just handily available for us in this table. And I'm actually going to leave that y, take it out of the table for a moment, but we'll come back to it in a second. Right, what else do we need in this table? We need a, that will be a meters squared. Again, that will be the average value. I'm going to leave that and just say we're going to calculate all these in terms of the average y. Okay, wetted perimeter in terms of meters, r, hydraulic mean radius in terms of meters. We're going to do 1 minus fr squared. We're going to do s0 minus sf, and then we're going to calculate a dx. Okay, that's what we need in our table. Let's just do a bit of tidying up in the table. Well, let's we can sort out this. So I'm making a mess here. Plus 1. So we're gonna do 10 steps down to 8, 9, 10 down to here. We're gonna have so I'll do a table that big. Okay. There's some all the borders in. Let's separate that out. So thick box, okay, just so it's slightly separated. Okay, right, the first value we're going to put in here is the y. Now I started by putting in this initial y, but actually what we're going to want is the y between the first and second depth. So let me just do a sketch here. So we're gonna we've got our dam here, and this is 5 meters, and we have chosen a delta y. Let's change the color there. We've chosen a delta y of minus 0.256 meters. And what we want to do is work out the place where the value of x, where this crosses. This is the delta x, or that delta x up here. It's that distance we're trying to work out. We've got a delta y that we're putting in here, but actually we want to calculate our values at the midpoint here. Yeah, and that we call our y average, which is going to be put in here. So we know this y here, we know this is y0 minus or plus delta y. So the average is y0 plus delta y over 2. So let's just go back to the table. So we'll put the average in between this point 0 and the next point. So that will be 5 plus delta y over 2. Okay, so it's 4.872 is the y in the middle of between the 0 and 1 integration points, and then we just calculate a, p, r, etc. based on this y, and that will give us average values for here. So I'm going to put actually in here based on average value of y. Okay. And just got that in there. So a bit of information on the table to help you realise where I'm coming from. So area, easy calculation. We just put the formula in here. That's the area is the width times the depth. So width b, fix that times the average depth. Okay, p is equal to the width. Fix that. Remember fixing it, you press F4, plus 2 times the average depth. R is easy, it's A divided by P. We need to put 1 minus the Froude number in here, so we've got a formula for the Froude number squared. It's actually showing on the screen here, up here, so let's put that in there. So that will be equals 1 minus q squared, and the q is that constant q we've got, q, fix that, squared, divided by the width squared, b, fix that, all squared, divided by g, divided by y cubed. So that's a y. We need to cube that. Okay, you should just look at these numbers. Is that about right? So it's above. It's going to be less than 1 because the third number is less than 1. So it should be less than 1 but positive. S0 minus SF, let's calculate that. So S0 is the slope, we'll get that, we'll fix that. Minus SF, and the SF calculation is here. Let's put that in here. So n squared, let's go up, fix my n squared, times by q squared. Go back again, get the q squared, fix it, square it, divide it by r to the 4/3, divide it by a squared. That's that formula. Okay, you see that these numbers are going to be very, very small. Let's just check what we're doing with our units here. Well, r is a length measurement. I think we should be showing that about 3 decimal places. Third number, similarly, well, we'll leave it at 4. S0 minus F, very small, so perhaps we should be showing that as a scientific, or we have it at least 4 decimal places, 4 significant figures. Sorry, we could do it as a scientific notation. Not 3, we'll say 4 here. 3. So we've got 4 significant figures. Okay. Right, now we can just simply do our calculation for delta x, which is this calculation, because all our expressions here within this large bracket are now mean calculations. So the delta x will be delta y, fix that, times by, I'm going to put brackets on here. Oh, actually we don't need the brackets. 1 minus fr squared divided by S0 minus SF, return. Okay, 3 times 0.003. Right, I think that's in scientific notation. It's a bit easier to see this because it's about 300 in general. And how many decimals? Let's have reduce that to 1 meter and actually get rid of that line. Okay, so the delta x is 312 meters negative, so backwards up the stream. So we need to put in the value here, which will be x, the one above it, plus the delta x. So we're now minus 312 upstream. Okay. Next row is very simple. We first just have to calculate this y average, which will be equals the midpoint there, the average there, plus the delta y. Okay, you might think, why is it, need to fix it, why is it just not half the delta y? Because that's the value halfway between the next cell. It's actually the next iteration point. So let me draw the on the pen. Here it'll go to the next y-av. Okay, so that's why it's the 4 value. Let me just go and put that in there. I'm mixed up on our pens, but this will be y, which is the y average from our previous cell, plus the delta y, which I'm going to fix. Okay, so why it's suddenly got much easier, we can just drag that cell down. And to do the full integration, we can just drag all this cell right down here. This actual last line isn't used, but what we get from our calculation is that 10 steps from 5 meters to the normal depth. So let's just put in here the normal depth will be that y plus a half of the thing. It's 2.44. That was our normal depth. I'm just going to colour that in because it's not the same y average as the ones above it. Okay, we just added a half. That's not the average. Those are corresponding y values and x values at the same point. So the solution is 10. After 10 iterations, we'll get 5, 8, 5, 4 is the number. What's that in reality? What's it's telling us? It says normal depth 2.44 is achieved 5.854 kilometers upstream from the dam. Now, I think that's not quite. Yeah, that's exactly what we have in the calculation, in the question solution for 10 steps of integration. We could do 2 steps of integration. I could quickly change that to 2. I'll put 2 in here. Let's go down the calculation. We're only interested in the first 2. That makes no sense. It says it's 4 kilometers, 469 meters, which is what the solution is there. As the table's built for 10, I'm just going to reproduce 10 and leave it on there. Okay, so that's how to build a backwater integration, an integration of the gradually varied flow equation based on an averaging method for which is a direct step method using a fixed delta y, a fixed y change to calculate the delta x. Another calculation might be you do a calculation for the delta x using a fixed delta x and get delta y. Okay, so we use this y average. That's not the only way of calculating this solution, and a further video may show you an alternative way of calculating the average value. Okay, thank you.